In the previous session, we had looked at a type of information source that is called as the Markov source. Okay. The characteristic of the Markov source is that it has a memory, right? And when we say we have a memory, the idea is that it can recall what are the previous symbols that were generated by the source. So when we say we have a memory, the uh, one peculiar feature associated with that memory is that the uh, next symbol that is getting generated will be dependent or will be affected by what was the previous symbol. Okay, so the one best example is intersymbol interference, right? Any symbol you receive that has the effect of all the past symbols. Okay, so we don't write simply p of x, it's p of xi, or p of xi will not be written as it is, given that there is a line followed by you write what are the previous symbols. Okay, so receiving p of xi, given that s1, s2, s3, sq have been already received. Okay, so that's the representation. And after that, we had seen the equations to be used for entropy. That is, hi is the entropy of a specific state, right? Every symbol is emitted by a state, and the state has an entropy associated with that. That is hi, right? We can try to calculate hi using this, and the entropy of the source can be calculated by using this particular formula, that is h. Okay, so there is a mistake, I will just correct that. Okay, so it's this term is not hi, the term should be simply h. Okay, so this is h is equal to summation uh, from I to n, uh, probability pi into hi. Okay, so that's the updated equation, kindly note. And then we have an equation for average entropy per symbol that can be calculated, right, as gn equal to 1 by n summation over all the i's, p of probability of mi, and log to the base 2 of 1 by p of m. The same equation, which can be written as h of s to the power n, the extension of the source, divided by capital N, where capital N is the total number of symbols. All right, so anyway, these are the equations, right? I'll show you how to use them. We'll solve problems based on these concepts today. So this is the first question. For the given state diagram of a Markov source, calculate the following. So part A of the question is the state probabilities. Part B of the question is to find the entropy of each state. And C, the last part of the question is entropy of the source. And here is the given state diagram. So we have four states basically. First state, another state, state number three, and say this is the state number four. Okay, so let's give some names to the states. This is state A, B, C, and D. Okay, so the probabilities are marked like this. From A to A, you have a probability of 0 0.6. If you are in A, then you can go to probability of, sorry, you can go to B like this with a probability 0 0.4. So you are in B, you can go to the state C with a probability 0 0.5, and from B you can go to say D with a probability of 0 0.5. Okay, so from C you can come back to C. So that probability is 0 0.6. From C we can move to D. That probability is 0 0.4. Similarly, from D we can go to B. Okay, so that is 0 0.5, and D we can come to A, that is also 0 0.5. Okay, so this is the given state diagram. In the sense, maybe here, this is how you try to analyze this. So there are four states indicates that the source, now it's a Markov source, it has memory, and you can see that it's going to emit four different symbols. Okay, the four symbols are A, B, C, D. Right. So if you are considering a non-Markov source, that means without any memory, normally we used to write, okay, there is a source which emits four symbols with these probabilities, P of A equal to B equal to C and D, right? That we used to write directly, where the emission of A, B, C, D are statistically independent. They are not dependent on. Now you see, here I'm trying to explain how we can say that this particular Markov model is dependent on the previous state. For example, right, let me assume that the current symbol is B. There is 50% chance that the previous symbol is D, or 40% chance that previous symbol is A, because from A I can come to B with 40%, and from D I can come to B with 50% chance. Right now you see, if it is C as of now, current symbol is C, means next symbol may not be B. Okay, that is because right now current symbol C, next symbol could be C or D. Correct. So because of this reason, right, we say that it has memory, it remembers what the current symbol is, and depending on that, right, it will generate a next symbol. In the sense, past symbol will be remembered to generate the current symbol, and so on. Okay, right. Now, so let us try to answer the first part of the question, that is calculate the state probabilities. Okay, so to calculate the state probabilities, we'll use the following uh, representation. Okay, this is the equation to use, right? So okay, so I'm trying to answer part A of the question. So let us try to calculate the probabilities of P of A, P of B, P of C, and P of D. It's not a straightforward calculation in case of the Markov source, right? We need to do a little bit of mathematics. Okay, so first, our first idea is that we'll try to write the equations that, right, it's called as a state equations, right? So we'll start with the writing the state equation. To write D. Let's write the state equations first. That means what is probability of A? Let's try to write. Probability of A means this is how you'll start. Start with any one source, that is any one state, sorry, any one state. In what all ways you can reach that state, you are going to look at that only. So that means this I'm not going to look, I'm going to consider this and this, because I can come to A state either from D or from A itself, right? That's what I understand when I look at this equation, when I look at this particular state diagram. So what I drew, so the chance of reaching A, that is probability of A, equal to, so look at that, already I should be in A, then only I'll be able to reach that. 60% of the time you come from P of A, okay, plus zero point 0.5 times you might come from D. Okay, this is equation 1 form. Like that, you write for all the states, that gives you the state equation. Okay, so let me write for the second one. If you look carefully, P of B I can write. So 40% of the time I'll come from A, and I'll come from D 50%. Okay, zero point 0.5 P of D. Let me call this as equation 2. Now I'll write for C, just check what I'm going to write. So for C, I can come from B 50% of the time. From C itself, I can reach C 60% of the time. Okay, so that will be. So let us look at the C now. So how do I reach C? 0 0.6 times probability of C plus 0 0.5 times probability of B. Correct? So let's write that. So P of C is equal to 0 0.5 times P of B plus I think 0 0.6 times should be written. So 0 0.6 into P of C. Okay, I'll call that as 3. Then I should write P of D. Let's go back and check what I should write. So D can be reached from C and B, right? So from C 0.4, from B 0.5. 0.5 into P of B plus 0.4 times P of C. So that is equation number 4. Now I have 4 equations and I have 4 unknowns. Okay, so let us try to do a calculation. From 1, I can try to write a relationship. That is P of A minus 0 0.6 P of A is equal to 0 0.5 P of D. Correct? So I can try to write P of A. I can take it common. 1 minus 0 0.6 is equal to 0 0.5 P of D. Correct? So that means I'll get a relationship between P of A and P of D directly. So P of probability of A is equal to 0 0.5 by 0 0.4 times P of D. So what is, it's a 5 by 4. I think 5 by 4 is 1.25. Okay, 1.25 P of D. So P of A and P of D I can interchange if required. So that is what I will write as equation number 5. Okay, now this is what I'll try to put in maybe another equation which contains A and D. Okay, let's put 5 in equation number 2. You can see equation number 2 has P of B, P of A, P of D, out of which P of A and P of D I can relate. Correct? Wherever I see P of A, I can put 1.25 P of B. So 5 in 2. Right on the left hand side, I have P of B. This is equal to, it says it is 0.4 P of A. So 0.4 into P of A is nothing but 1.25 P of D. Okay, plus I have another term, that is 0 0.5 P of D. So just see, this is what after the substitution of a 5 in equation number 2. Okay, I replace this P of A by 1.25 P of D. Then we have zero point 0.5 P of D as it is. Okay, so once that is done, now we can try to relate the P of B and the P of A. Okay, so let's try to uh, do that. So P of B is equal to, so zero point 0.4 into 1.25 is 0.5. Okay, so zero point 0.5 P of D plus one more 0.5 only, right? Okay, so that means they are equal. That is equal to P of D. So P of B and P of D are equal. Okay, so that is what equation number 6. All right, so we will see what else we can do. Equation, yeah, you see equation 3, we have P of C and P of B. We can try to relate them as well. Okay, so 3 gives, so on the left hand side I have P of C, right hand side it is a zero point 0.6 P of C plus zero point 0.5 times P of B. This is what I have. Okay, so P of C minus 0.6 P of C is equal to 0.5 P of B. I think we are going to get the same relationship once again, which we got between A and D. So P of C is equal to zero point 0.5 by zero point 0.4, that is 1.25 P of D. Okay, so that is equation number 7. And we have a P of B and P of D we can substitute. Okay, so let's try to convert everything into P of D itself. Okay, P of D. So 6 in 7 gives me P of C is 1.25 P of D. Okay, so that is 8. Okay, now I know that out of the 4 symbols, only one symbol will be generated at a given point of time. Are you okay? Right? In whenever this machine generates the symbols, one of them will be generated. So the sum of all the symbols, the sum of the probabilities of generation of the symbols should be equal to 1. That is, that cannot be violated, whatever may be the source. Okay, so we start from that. Now we try to find the relationship between each other. Okay, so we know that probability of A plus probability of B plus probability of C plus probability of D is equal to 1. Okay, we know that. Now we see everything, we try to convert that into in terms of P of D itself. P of B is P of D. P of A is 1.25 P of D. So let's try to substitute. Okay, so P of A is 1.25 P of D plus P of B is P of D itself. Okay, plus P of C is 1.25 P of D plus P of D equals to 1. So I can directly calculate what is the, okay, 1.25 is 2.5 plus 1 3.5 plus 1 4.5. So 4.5 times P of D equals to 1. All right, so calculate what is P of D then. Okay, P of D is 1 by 4.5. Please calculate. So this is equal to 0.4. Right. Then this means I can actually calculate P of A directly. So P of A is equal to 1.25 times P of D, 1.25 into 0.4. This is 0.5. I have, because this, when we add P of A plus P of D, it is almost zero point 0.9, correct? So I think I have a doubt in that. So this may not be possible. So calculate P of D once again. right? 1 by 4. Okay, or you do one thing, right? So keep it in the fraction format. That's also will work. Okay, so I'll tell you how to do that. This is not zero point 0.4. So 4.5 is 9 by 2, correct? Half of 9. So I'll try to write in this way. So this is equal to 1 divided by, this is 9 by 2. The 2 goes to the numerator. So this is 2 by 9. You can keep it in this format, no problem. Okay, right. So also now this changes. This is 1.25. 1.25 times this is 2 by 9. Okay, so 1.25 into 2 by 9, let's calculate. That is 5 by 18. 5 by 18, or yeah, what's that? When you try to convert into uh, this is 0.2778 if you want. Okay, in that form. So otherwise the previous one will be this is equal to 0.2222. Okay, right. P of A and P of D we got. Similarly, we know the relationship, right? So that is P of B equals to P of D, right? So that will be 0.2222. Right. Then we have P of C that is equal to P of A, right? P of A, which is 1.25 times P of D. That's what we have as 0.2778. Now do one thing, simply calculate the sum of them just to check that whether you get close to 1. Maybe you get 0.9999 or something. Okay, possible. But right, it's expected that you reach 1. So to verify whether these probabilities we obtain for each of the states, whether they are correct or not, when you sum up, you should get 1. Okay, so now we are getting 1, so we'll proceed. So first part of answer is over. So the questions, if you can see, right, the first part of the question says, find out the state probabilities. This is done now. I got all the states probabilities like this. So the next thing is that I need to find the entropy of each state. Okay, so let me write a general equation for that, which we can apply to any problem to solve. So this is part 2 or B in the question. So to find entropy, okay, this is entropy of state, any state I, right, can be calculated. This is denoted as HI. HI is equal to summation I varying from 1 to n. There are n states. This is the probability of moving from ith state to jth state log to the base 2 of 1 divided by Pij. It's the same equation which we had written earlier. Okay, but now you see, I'll try to write the specific case. So HA, entropy of state A, is equal to summation. You see, I is equal to 1. How many other states you have? Sorry, how many total states you have? 4 states, right? It is probability of moving from A to jth state, any jth state. Okay, sorry, this is actually J varying from 1 to n. Okay, all the other possible states. It's not I, sorry, it's J. Hi is equal to integral, summation J varying from 1 to n. Okay, so Paj log to the base 2 of 1 divided by Paj. So I'll expand that. Now I know that in the given state diagram, we have 4 different states, correct? So first one is probability of moving A to A. That is the first state. Log to the base 2 of 1 divided by probability of moving from A to A, plus what are the other options you have? Probability of moving from A to B, log to the base 2, 1 divided by probability of A to B, and so on, plus P. I may have A to C connection, log to the base 2, 1 divided by PAC, plus P, last one, A to D, if you have a connection, you will fill this. But equation is just like that. Okay, so log to the base 2, 1 divided by PAD. Now what I do, I'll go, this is just expansion. Now I'll go back to the given state diagram and understand that what are the various terms I can substitute from A. So now you can see that this zero point 0.6 is there, right? It is PAA. A is my current state, A to A transition. Okay, that's what is PAA. Yes, I have a term PAA and I can substitute there zero point 0.6. Is it okay? Then, so I can check what else I have, right? Do I have a connection A to B? Yes, I have. So A to B is PAB, that is zero point 0.4. Then I don't have any connection from PAC. Okay, A to C, no direct connection. So PAC is 0. There is no probability, right? Similarly, A to D is also not there. D to A is there. Okay, so that is PDA, not AD, right? So PAC and PAD are 0. Other than that, the two more terms I can write, which are PAA and PAB. Okay, PAA is 0 0.6, PAB is 0 0.4. So from this diagram itself, I'll be filling up this. So that means this is equal to, so PAA 0 0.6, 0 0.6 log to the base to 1 by 0 0.6. AB is there, 0 0.4 log to the base to 1 by 0 0.4. So next term, PAC is 0, PAD is also 0. Okay, simply calculate this. So we get this is HA. Okay, HA is represents the entropy of state A, right? And when we simplify this above equation, we get 0 0.971, right? It's H, right? So bits per symbol. Okay, the A has this many. This is the entropy information content. Okay, similarly, let's go ahead and calculate HB. So for HB, it's the same equation. Probability of moving from B to A log to the base 2 1 by P of BA plus P of BB log to the base 2 1 divided by P of BB plus P of moving from B to C log to the base to 1 divided by PBC plus probability B to D log to the base to 1 divided by B to D, right? So let's go back and check the state diagram for the terms. So from B, I can move to C. From B, I can move to D. No BB, no BA. Okay, so 0.5, 0.5. So first two terms are 0. Okay, 0 plus 0 plus 0 0.5 log to the base to 1 divided by 0 0.5 plus 0 0.5 log to the base to 1 by 0 0.5. Please calculate this. So this is equals to HB equals to 1. Now we'll calculate HC, entropy of the third state, that is C. So right, it'll directly go and check and directly write. No need to write the equation. So I wrote the equation just to make you comfortable with the right what we are trying to write. Okay, from C to C I have, C to D also we have. In the sense, no C to B, no C to A. Right, only the terms which we have will write. So one is 0 0.6, other one is 0 0.4. Okay, so this is equal to 0 0.6 log to the base to 1 by 0 0.6 plus 0 0.4 log to the base to 1 divided by 0 0.4. So this is equals to 0 0.97 bits per symbol. Okay, then we go to okay, HC is over, right? So we'll go to HD, that's the last state. So let's quickly check the state diagram. From D, I can move to A and I can move to D. Sorry, B. From D to B, D to A, we have. So both are zero point 0.5. I think we get the same answer which we got for the previous case, that is HB. So HD is equal to 0 0.5 log to the base 2 1 divided by 0 0.5 plus 0 0.5 log to the base 2 1 by 0 0.5, that is equal to 1. Okay, bit per symbol. Right. So we answered the next question as well. That's right. These two are over. Entropy of each of the state is over. The next part is entropy of the source. Entropy of the source, that is H, is equal to, for all the states, I is equal to 1 to n, probability of each state into H of that state, right? So H is equal to, in this case, it is I varying from 1 to 4, every probability of a state into its. So it's like PA HE plus PB HB plus PC HC plus PD HD. Every value we have, we already have calculated. Let's simply substitute that, right? So PA, I think let me just check the value. PA is 0.2778 is a probability, into HA is a 0.971 plus probability of B is a 0.2222 into HB is 1, 0.2778 into 0.971 plus 0.2222, that is probability of D into PD into HD. Okay, please calculate this. So this comes to be 0.9839. Since it is entropy, it's once again bits per symbol.